Hi, everybody. This lecture is the final lecture of Chapter 2 in Electric Circuits, and it will cover sections 2.4 and 2.5. So I wanted to bring a couple of things to your attention on our Moodle page before we get started with the lecture itself. But a couple of things that are really important are up at the beginning. I have put the passive sign convention usage. And the statement is whenever the reference direction for the current in an element is in the direction of a voltage drop across the element, use positive sign in any expression that relates voltage current, otherwise use a negative sign. What that means specifically, voltage drop means going from positive to negative on the battery or whatever is the current element. So if the current moves in the direction of a voltage drop, so in other words, if the voltage moves from positive to negative, you use a positive sign in anything that relates, for example, V equals IR or whatever. So if, on the other hand, it does not move in the direction of a voltage drop, if the arrow goes from negative to positive, then you use a negative sign. It can be a little bit confusing for a couple of reasons. One of the reasons is that there are a lot of times where if you have familiarity with electrical appliances or elements in real life, we don't really call things negative or positive in this way. Often we just say positive, like we say something makes power, whatever. We don't talk about absorbs. We don't talk about absorbs as being positive. We talk about maybe delivering power as being positive. But in order to make the math work, this becomes crucially important that you follow the passive sign convention. All right, so having said that, I just wanted to make sure when we reference this. The other thing that can be kind of confusing, in my opinion, is that in these early chapters of the course, often the arrow of current will be drawn in a somewhat arbitrary way. So it's not necessarily the way that the current actually flows. It's just drawn that way so that you have a reference to use this passive sign convention. But whatever it is, just like in other classes we've talked about, for example, in statics, if you choose a sign convention, like if you're doing an analysis of a truss, and you realize halfway through that you are incorrect, you have two choices. You either stay with it and let the signs work themselves out in the math, or you change it and start all over again. So it's the same here. Once you draw that circuit, stick with that sign convention no matter what. All right. So having said that, when we talk about chapter 2 and we talk about the circuit elements, we can use Ohm's law. We can use Kirchhoff's current law and Kirchhoff's voltage law. And then we also use these to solve circuits. And we talk about resistors, we've talked about the units, and so we understand how everything works together. So let's take a look at a couple of simple circuits that we will be talking about in the future. Okay, what we have here, it asks us to find I sub 0, which is the current across the 10 ohm resistor. Now, here's the deal. We have an independent voltage source. We know that because we have positive and negative, and we have an independent current source of 6 amps. We then have two resistors. One is 10 ohms and one is 50 ohms. So the first thing that we do is we label all of the unknown voltages and currents, because those are the three things that we're going to want to find. We have our resistances. Now we need to get the unknown voltages and the unknown currents. Then we can use Ohm's law, KCL and KVL, to write the equations that will help us to solve this circuit. Okay, so right here we know that I sub 0 is passing over the 10 ohm current, and we know something about the voltage, or maybe we don't. And similarly here, we have something about a current and something about a volt. Now, just before we start the actual analysis, we know that amperage or the current is going to have to add up in a certain way on the nodes. We also know that the voltage is going to have to behave in a certain way. And those certain ways have to correspond with Ohm's law, KCL, and KVL. So the first thing is we can take a look at the 50 ohm resistor, and we know that V is equal to IR. So we know that V50 is equal to 50 times whatever the current is right here, which has been labeled I50. And sometimes I'm a little irritated by their subscripting, but I've tried in the past to change subscripts to match something that seems more intuitive to me, and it always ends up in disastrous, confusing mess for the students. So I'm not going to do that. So we're going to stick with these subscripts. So the current that passes over the 50 ohm resistor is called I sub 50. The current that passes over the 10 ohm resistor is I sub 0, because that is given in the problem. All right, so KCL tells us that if we look at node A and we think about the currents going in and out, we have I sub G leaving, and we have I sub O leaving. Now, is that really the direction of the currents? Maybe, maybe not, but that is how it is given in the problem. So we say that the currents leaving have to equal 0. And here at node B, we have I sub 0 entering, and we have I sub 50 leaving, and we have the 6 amps also coming in. So I have 3 currents. This one is entering, this one is entering, and this one is leaving. So if you look at that, that's what this sign convention means. You could also say entering I sub O, entering I sub 6 minus I sub 50, because it's leaving, is equal to 0. Works the same way. All right, so then the KVL, we take a look at we talk about what's going on each one of these closed loops. So this closed loop, the one on the left, we have a voltage of 120. Why is it negative? Well, because I'm not going to talk about that for a minute. I don't really like this, but that's okay. So we have the I sub G going from positive to negative. We have the voltage in the 10 ohm circuit, and we have the voltage in the 50 ohm circuit, and they have to add to 0. On the right, we have the 6 volts, which is going from negative to positive. So this is actually backward from the statement of the passive sign convention. Do you see that? I sub G is going from positive to negative. So according to passive sign convention, that would actually be a negative, but we're calling it positive. And then we're doing the same thing here. So it still works out, but it's not consistent. Here we have 6 going from negative to positive. We're calling that positive because it's going from a negative to a positive, just like we did over here. And then we have the 50. And we also have, well, here's our 6. Here is, I'm sorry, here we go. Negative going over the 50 from positive to negative. Positive from going through that independent source equals 0. All right, so then we're going to solve. We can, now that we have all these variables, we can solve, we can put them together, we can substitute, and we can come up with an expression that I sub 0, which is right here, is negative 3 amps. Okay, so what does negative mean? It means it's in the opposite direction of I sub G. Okay, so here we go with another one. Let's just take a look. Before we start calculating power, let's try to predict which element will be supplying power. Okay, here we can't really tell. We don't have enough information in order to do this circuit. All right, but continuing on here, we now know that we have 3 amps here, and we have negative 3 amps here. We have positive 3 amps here, and we have 6 amps over here. We calculate the power, and the power has to add up to 0 for the whole circuit. So we take the 120 times 3, positive. Then we have to go I squared R, which is always going to be positive. The resistors are always going to be positive, right? Same here. 3 squared times 50. Those are both positive. And then here, we're going to have voltage times current, which is a negative. So this is a negative 900. And if you add these together, you get a value of 0, which is required for any circuit. All right, now we're looking at, let's take a look back here. This is the one that we just did. I want to look at right here. Okay, so we have a 10 ohm and a 50 ohm. When we go to our next circuit, we have an unknown resistor. Here we have 120 volts over a 24 ohm resistor, and we have an 8 ohm resistor over here. So here it says, can we predict which elements are going to be supplying power? Well, resistors never supply power, right? Resistors always absorb power because they're positive, so just the source. That also means that we have to think about this. If we're thinking about the resistor power as being positive, we have to think about the voltage or the power in the universal, in the independent source as being negative in order to make that power equation work out. All right, so here is a different circuit. We have an independent voltage source of 5 volts. Here we have an independent voltage source of 8 volts. And here we have an independent voltage source of 1 volt. We then have a dependent voltage source, which is unknown, and we have 3 resistors. So as you can see, the current arrows have been drawn so that we can solve for that. We do the voltage law on the left loop, which is going to be -5 plus the 54,000 I plus minus 1, because that's just voltage, and then the I6 times that 6,000. Now, once again, remember, kilovolt is 1,000, so this is 6,000 ohms, this is 54,000 ohms. So those are pretty significant resistors, but also you just need to keep that sign straight. So make sure, or excuse me, that magnitude straight. So always take it back to base units. So we have -5 plus 54 times I minus 1. You notice the sources, we go from negative to positive, right? And then here, this is going to be positive again, because once again, it's a resistor and the resistors are positive in that sense. Okay, so the Kirchhoff's current law, on the top, we take a look, I guess you're going to call this the top. If you want to call that node A, you're going to have the currents coming in, I1 and 30 I, and then you have I6 going out. So you might say plus, plus, and minus, or the way that they've done it is that we have 6I or I6. So in other words, they're just saying the currents in equal the currents out. Or you could say the currents in minus the current out has to equal 0. It's mathematically the same thing. So we can simplify that to I6 is equal to 31 times I. Then we can combine those equations and solve, and we get some significant answers. We get I sub 1, which is right here, is 25 microamps. That's 10 to the minus 6. And on the using KVL on the right, we get that the voltage is right here is a -2 volts. And I just want to really be clear, this, once again, their use of variables is not, it's a little bit messy. So this is V. Here we have a scrolly V. I would like to see them look the same, but you're all intelligent people and you can pick up on what's going on. So in other words, we're talking about this V. I would like this V to be a script V to look the same, to keep that straight. All right, the final one we have to do a power balance, because once again, sum of all powers has to equal 0. So we calculate the power on each of these elements. We give them the proper sign, whether power is absorbed or power is produced. And then we add the powers together and we come up with 0. Now, once again, these are all in microwatts, which is a wee little tiny bit of power, but they all have to add up, and they do, and we are successful in our analysis of this circuit. Okay, so like I said, I think this overall, this textbook is very, very good. I think there are just some things that are a little bit confusing, so I try to make a point to show those to you so that you will be aware, and just sort of if something strikes you as a little confusing, then perhaps you will just refer back to my lectures, and that will help you to sort things out. Now, finally, the last thing that I would like to do is to show you at the end of chapter 1 and at the end of chapter 2, I've also included a sheet that shows the important formulas. Okay, so here we have Ohm's law, we have power across a resistor, we have Kirchhoff's current law, and Kirchhoff's voltage law. So those are like the heavy hitters. And really, as you progress through electric circuits and further into your courses in electricity, these are still sort of the heavy hitters. And so if you use these and you're fluent with them, you're not going to do a bad job. All right, so that is the end of chapter 2, covering sections 2.4 and 2.5. I will post the homework for those once again on our Moodle page, and that will be the complete set of homework. There will be a set for 2.1, 2.2, and 2.3, then 2.4 and 2.5, and that will be it. So when the due date comes up, you'll have all of the homework that you need to submit. So in the meantime, we will meet for lab on Wednesday as usual, and I'll be available to you if you need my help in between. All right, have a great day, everybody.